In this video, I wanted to take a look at interfacing the Arduino to the Sharp IR distance sensor that you all are using in Mini Project 2. Some of you, in working with the sensor so far, have noticed like outliers or little spikes every so often that are not, it's not apparent where they might be coming from. And so I'm going to take a closer look at those spikes and see if we can come up with a reasonable way of reading data from the sensor in a way that is much cleaner and will not have those same sort of spikes. So here, my hardware setup, I have the Sharp IR distance sensor connected through the breadboard over here to +5 and ground, and the white wire is the output, and I've got that connected to pin A0 from this purple wire. And I'm making these connections in the breadboard here because I'm also planning on taking a look at the analog or the sensor output using my analog discovery as an oscilloscope. So we can see kind of what's going on in a little more detail. But to start out with, I just want to take a look at what the readings look like in a tool called the serial plotter. And so I've created a sketch that I'll be pushing out to my Arduino that sets up a basic loop time of 20 milliseconds, and it opens up a serial port at 115.2 kilobauds. And what it's going to do is it's going to take a reading. Actually, it's going to take 3 readings from the sensor, and at first we're just going to take the first one and print that out to the serial port and take a look at the sequence of values using something called the serial plotter. And some of you may have done this, some of you may have just printed the numerical output and used the serial monitor to display the number. And you saw a similar kind of thing to what we'll see, but we'll push this out. And we'll start the serial plotter. And you can see that we have every so often a spike. So the readings are hovering around here around 90, but then every once in a while there's a spike up to 150, which is a pretty significant spike. And if I put a target out there and move my hand farther and farther up, you can see that it doesn't happen every reading, but every so often, maybe like 10% of the time, we get this annoying spiky thing. And so that spike is likely to be the cause of some of your outliers and your calibration curves, and it's just generally creating a huge perturbation, and it's going to be a headache for us. And so one thing that you might try is just a simple averaging. So let's say we take 3 readings. We could compute the average of those 3, and that will have the effect of reducing the spike, but unfortunately it won't get rid of it. So you can see here with averaging, the spikes are still there, but they are a little bit smaller than they were. Probably about 1/3 the height, strangely enough. So that's a help, but it's still not great. So what we'd like to do is to take a look at the actual what the analog output of the sensor looks like on an oscilloscope, and see if there's any structure that we might be able to somehow exploit when we do this reading to clean that up. So let's close down the serial monitor here, the serial plotter, and start up waveforms, which is the software for the analog discovery. So we want a scope, and we're going to maybe make this smaller. And let's put this away so we get a little bit more space. And let's do oh, I don't know, 5 milliseconds per division, and we want the range to be 1 volt per division. Don't really care about channel 2 so much, so let's turn channel 2 off because we're not even looking at it. Move this down here. Trigger doesn't really matter, but put the level up to 2.5 since that's halfway between 0 and 5. And let's run this and see what we can see. Well, that's interesting. We got little pulses on our waveform. Okay, so let's zoom in here and see what that looks like. Maybe let's do 200 millivolts per division and move this up. And zoom in time. Let's make it, I don't know, 1 millisecond per division. Oh, okay. Let's see if we can get a stable waveform here. So I moved the trigger level down so it goes through the waveform here, and you can see that it looks like what we're looking at here is a signal that we can move up and down depending on how far the target is away from the sensor. But it looks like there's this 1 millisecond waveform that's kind of superimposed on that, and kind of looks like it's an upward going spike that is maybe like 120 microseconds long. So there's nothing in the data sheet that indicates that that should be the characteristic of the output of the sensor, but I have used a couple of different sensors and they both exhibit the same type of behavior. And so what can we do to mitigate this issue? So this happens about looks like 120 or 130 microseconds. Once every millisecond. Well, if we were to somehow be able to synchronize our analog read to this little pulse in the output signal, we could somehow sense when that begins and delay by half a millisecond or so. We could always make sure that we avoid this pulse. But what's happening with the little spiky things, now seeing this, is probably that as we sample it, once in a while we're going to sample it in this little pulse, and so we're going to get a systematically higher reading. And if we sample it, most of the time, somewhere between 85 and 90% of the time, we're going to sample it in the low part of the waveform here and not on this little pulse. And so that's why we intermittently get this reading that's a little higher than the rest of them. So what can we do about this? So we found that when we time to analog read, it takes about a little more than 100 microseconds to actually do an analog read. And so if we do 3 analog reads in a row, there's a chance that we may get 3 all within this low spot here, or we may get 1 in the high time here and 2 in the low time. We may get 2, I suppose there's a chance that we'll get 2 in the high time and 1 in the low time. But if we take 3, and we take the minimum of the 3, we should be guaranteed to be in one of these low spots. Right? Because given that this is probably slightly longer than it takes to do an analog read, there's a small chance that we'll sample at the very beginning of one of these little pulses and at the very end. But then the third one will be either before or after. And so I think if we take the minimum of the 3 readings, we will achieve what we want. I suppose the other option would be to put a little bit of delay, and this would only need to be like 20 microseconds of delay, and I'm not even sure. Certainly the delays function that takes some number of milliseconds is not going to cut the mustard there. But if we were to figure out a way of actually putting in some number of microseconds of delay, we could probably do with just 2 readings or something and take the minimum of 2 readings. But given that the analog read takes a little bit less than the width of the pulse, we may get 2 of the readings be during the high time. So let's get rid of this and change this to res equals min of x comma y comma z. So min is a function that's built into the Arduino libraries, and it takes 2 arguments and returns the minimum of those 2. So we can compose 2 minimums to get a 3-way minimum, and let us push that out. And let's get rid of the analog discovery. And do the serial plotter. Okay, so this is looking a little bit like there's still some spikies, but to put that in perspective, if we actually look at the signal on a bigger scale with a target out there, you can see that this is much cleaner, and we don't have the same kind of spikies that we had even when we were averaging the 3. So that's much, much nicer. I'm just moving my hand up and down between maybe 1 and 2 feet or so. So that's a fairly simple way of exploiting what we can learn about the signal from looking at it on an oscilloscope to clean up the reading quite a lot over what we were able to do not knowing anything about the signal. And this is nice because we don't have to be synchronized to the spike in the output or know anything about when that's happening. And you can probably do even better by combining this idea of averaging with taking these readings so that you're guaranteed that some number of the ones that you take are not going to be within that high time. So I think if we were to somehow figure out how to add maybe 20 microseconds worth of delay here, we could just take 2 readings and we'd be guaranteed that one of them would be outside of the pulse, and we could take the minimum of 2 of them, or we could take 4 readings with a little bit of delay in between each one, and then take the 3 lower readings and throw out the maximum of the set and average the 3 and get somewhat cleaner data than we're getting here. But this is I think this is probably just fine given how clean that looks. So hopefully that's helpful and illustrates the value of actually looking at things with an oscilloscope. So thanks for watching.